All right, we are going to take a look at some introductory concepts for our chemistry class. What is chemistry? Chemistry is the study of the composition, structure, properties, and the change of matter and energy. Well, energy is the ability to do work, and matter is anything that occupies space and has mass. Remember that mass is the amount of matter that an object contains. And there's a difference between mass and weight, right? Depending on gravitational energy or gravitational force. So down here, I just have some examples of chemistry. I mean, when you're cooking, there is chemistry involved. There's a whole lot of different career options that involve chemistry, from being a sports scientist to a zoologist to a cosmetic scientist, a wine taster, a brewer, a geologist, a biochemist, marketing, doctors, pharmacists, all sorts of careers involve chemistry. Everything is chemistry. Chemistry is often called the central science. We have relevance in our daily life. It's an interesting topic. Career opportunities, biomedical applications, it benefits society. There's fun experiments. Even the American Chemical Society calls chemistry the central science. This is just another picture showing how chemistry is interconnected to so many other STEM disciplines. Why do we want to study chemistry? Because chemistry is everywhere in the world around us. It's in the food we eat, the clothes we wear, the water you drink, medicines. It's in the air, it's in cleaners. It's everywhere. It helps you understand the world that's around you, like why do leaves change color in the fall? Why are plants green? How is cheese made? What is in soap and how does it clean? Especially during this COVID time when everybody's telling you to wash your hands, wash your hands, wash your hands. Just having the basic knowledge of chemistry helps you read and understand product labels. What's in your food on those food labels? It can help you make informed decisions. It teaches you useful skills. Chemistry means learning how to be objective and how to reason and solve problems. It helps you understand current events, like I said, especially during COVID times, including news about petroleum, product recalls, pollution, the environment. And it definitely opens up career options that might not even be in chemistry, but if you have the analytical skills from chemistry classes, it is helpful. It applies to the food industry, retail sales, transportation, art, homemaking, any type of work. I bet you could apply chemistry to it. So here are some examples of chemistry in everyday life. You do have a discussion prompt this week. So maybe you can get to thinking a little bit more critical about how chemistry is in your life. So here's 3 representations of matter. We can see matter at the macroscopic level. For example, this table salt. We can see that, we can observe it. We can measure that. We can touch and have the senses. We see it at the particulate level, meaning the individual particles, molecules, ions, atoms. We can't see that, but that's the particulate level, the particle level. And we symbolize it, like we can write salt as NaCl. So it's the written representation part of chemistry. The term used for an investigation that entails performing an experiment, proposing a hypothesis, testing that hypothesis, and stating a theory or law is called the scientific method. This is highly, highly used in all science. Now, how do we apply the scientific method? We have a theory that explains the behavior, the nature, or the natural law that states a measurable relationship. And this is through tested time after time after time again. And there is a planned strategy to make observations under controlled conditions. In this class, we will not be making any theories or laws, but we will do some studying of them. So, speaking of matter, atoms are the smallest particle of an element that has the properties of that element and can enter into a chemical combination. A molecule is two or more atoms that are connected by strong forces called chemical bonds. So we will be looking at and using the periodic table to see these different atoms. For example, the elements of hydrogen, oxygen, phosphorus, and sulfur all form molecules consisting of two or more atoms of that element. So here I have two hydrogen atoms together, and here I have two oxygens, and here I have 4 phosphorus and 8 sulfurs. Those are molecules. If I just have an aluminum, one aluminum, that would be an aluminum atom. When they're two or more of the same atom together, then they are molecules. Then we have compounds like H2O, water, carbon dioxide, CO2, and glucose. They have lots of different combinations of atoms of different elements. So this is going to be called a compound. So here I have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms to create that glucose. Now we said chemistry is the study of energy too. We have 2 different types of energy that we'll be looking at: kinetic energy, which is the energy of motion, and potential energy, which results from position. So kinetic energy, the motion at the particle level, especially thermal energy. And we're going to be talking about that when we get into heat and temperature especially. And even when we're talking about solids, liquids, and gases. And as that temperature increases to make those particles move from just being moving slowly in a solid to moving faster in a liquid and to moving very fast in a gas. Other forms of kinetic energy is like throwing a baseball, falling water. So matter consists of atoms and molecules that are in motion. There's kinetic energy associated with that. Potential energy, there's gravitational potential energy that results from being held at a particular height, waterfalls. It's also potential energy that is stored in a spring, stored in molecules, especially stored in food. We're going to talk about energy when we talk about heat and how that is stored energy. And we also have potential energy associated with the charge of particles and nuclear energy. So here's an example of a diver standing at the top of their diving board. They have potential energy. So they're at a gravitational height. Then as they start to dive, they convert that potential energy into kinetic energy. And when they hit the water from that impact, there is heat and work that is produced, thermal and mechanical energy when they dive into the water. So lots of conversions of energy. Energy cannot be created or destroyed, but it can be converted from one form to another. So going back to our levels of matter, the macroscopic, observing the particulate level, looking at those particles, and then our symbolic, or our way of representing matter. When we represent matter, we can do it in 2 different ways. We can do it qualitatively and we can do it quantitatively. So qualitative is non-numerical. So in this case, we would say that this is a blue solid. It is granular. So it's based on our sight, our smell, all of our senses. Quantitative is a number. I would say I have 28.331 grams of that substance. Melting points, boiling points, obviously the mass, density, the temperature of something are all quantitative ways to macroscopically represent our matter. Symbolically, chemistry is definitely a periodic table-based symbolic tool. So we will be using this, and you will want to be sure that you have this handy for assignments, for quizzes, for proving grounds. There is a copy of this in the resource section on your Canvas page. So please make sure that you have a copy of this. At that particulate level, so we can see the individual particles that cannot be seen even with the microscope. Chemists often think about chemistry at the particulate level when we are conveying chemical compounds or whatnot. And this just gives us that visual, the way that they represented it, these atoms in spheres. So particles have mass and energy. We know that so this is solid ice, that is very low energy. There is stored energy in those bonds. They have very low kinetic energy. And when we add energy to that solid, so we add energy to it, we're able to have those particles move faster and more freely. So they break away from one another, and that's in that rigid form to create liquid. We add more energy, which causes vaporization. So then all of a sudden these particles are way far apart. Now if we take away energy, we have water that our water vapor that condenses to water. Take away more energy, and that causes freezing. So real quick, I don't want to spend too long on this, but looking at solids, liquids, and gases, we know that, like we said, matter is anything that occupies space and has mass. So the three states, or the three phases of matter, looking at solids, liquids, and gases. I'm going to go through this kind of quickly, so feel free if you need to pause the video or rewind and go back and look at this a little bit further. It might help you just remember. Here down here we have solids that has a definite shape. It is rigid. You can see even in that beaker there's a nice square of the solid. Definite shape, a definite volume, and very low kinetic energy. Low energy. Those you can see they're fixed positions. They are vibrating in place, very low, kind of like they're doing the, they're waiting at the bus stop for the bus in the middle of winter, and they're just shivering. Then they start to warm up. The weather turns nicer. People are out and about more. There is more energy than they are in liquid form. So they have an indefinite shape. They do have a definite volume, and it's middle kinetic energy. We add more energy. It's the middle of summer. There's so much energy, high kinetic energy. Indefinite volume and indefinite shape. It's going to fill the container and have the shape of its container. So a little bit, just more debriefing on solids, liquids, and gases. And I just want to show you a fun little animation here. Here we have our solid chunk. And when I add energy, so I'm in a solid form right now, we can see that they are arranged very tightly. They move very little. They're just kind of vibrating in place. I'm going to make it a liquid. So you can watch right here. The temperature goes up and it becomes a liquid. And we can see that they're able to move past one another easier. They're close, but they're not in that neat arrangement that the solid was. So we can see that it's in liquid form. We can see down here the heat was added. Now let's add more heat. Let's make it become a gas. Look at that temperature go up. And we can see that those gas particles are moving so much faster. There's a lot of space in between them. So just to kind of help you visualize. Again, another representation of our states of matter. And this is another showing the change of states going from solid to a liquid, that's melting, vaporization, going backwards, and then going directly from a solid to a gas, which is sublimation, and a gas to a solid called deposition. So make sure that you know those changes of states. So matter can be divided into two classes. They can be pure substances or they can be mixtures. So this is important to know. A pure substance is composed of only one substance and cannot be physically separated. Now a mixture is more than one pure substance. They can be physically separated into its component substances. So a pure substance is either an element or a compound. That is very important. So you have to ask yourself, is this pure? Is it an element? Can I find it on the periodic table? Is it a compound? Meaning, does it have a chemical compound formula? So elements that are together that cannot be chemically separated. So H2O, water, C6H12O6, AgCl, silver chloride, sugar, carbon dioxide, CO2, salt, NaCl. So pure substances are elements and compounds. Again, we know that it is a pure substance if it is found on the periodic table, so it's an element, or it is more than one element combined together to form a compound. Now, it is important to, you don't need to memorize the periodic table, but it will be important to know at least the names and symbols of the first 20 elements, plus a few others down here that are noted. Just because when we really start getting into looking at elements and compounds and those properties, it will be beneficial for you to be able to recognize that C is carbon and that Mg is magnesium and Cl is chlorine, and just to be able to recognize, like I said, the first 20 plus a few extras that are commonly used in class. So like we said, elements are pure substances. There are 118 elements recorded on the periodic table. We are going to look more at the periodic table in coming chapters. Elements are neutrally charged, and remember, of elements, an atom is the smallest unit of an element that has all the properties of an element. So we are going to talk about how atoms can be broken down even further, because we know that atoms have protons, neutrons, and electrons, but those do not have properties of that actual element. So the atom is the smallest unit of the element that has all the properties of the element. There are 7 elements that are not just H or by themselves. They occur what we say diatomically, which means that they are bound with themselves. So H2, so hydrogen is not ever going to be expressed by itself as just H. It's always H2. Same with nitrogen, oxygen, fluorine, and these guys. And I'm going to show you a little trick to help you remember these 7, and it's called Brinkelhoff. Brinklhof. Brinkelhoff. And that includes bromine down here, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Those 7 are always diatomic when they are by themselves. So you just need to remember Brinkelhoff. This is just a little bit more on elements, so feel free to pause or to rewind and look back at these slides. More about elements. More about element symbols. And this is just kind of interesting. I thought that almost 1/3 of naturally occurring elements are used to make a cell phone. From the case to the processor to the screen components to the battery components. I thought that was pretty neat. So our other type of pure substance is a compound. And like I said, it's a fixed ratio of elements. For example, water, H2O, always will have 2 hydrogens and 1 oxygen. We know that they can be broken down by a chemical reaction. We can take H2O and we can separate it into hydrogen gas and oxygen gas. Some examples: caffeine, water, carbon monoxide, nylon, rust. Rust is iron oxide. So these are all compounds. Now, when we have a compound, like I just said, H2O, we have it expressed in a chemical formula. And that chemical formula tells us how many of each atoms of each element are in that compound. So sulfuric acid, for example, has 2 hydrogens, 4 oxygens, and then there's not a number written past this S, so that means that there is 1 S. If there's no number, you assume that it's 1. So sulfuric acid, this compound has 4, 5, 6, 7 atoms. Some formulas have parentheses. So for example, this ethylene glycol right here, C2H4OH2. So we can look at this and we can say, okay, there's 2 C's and 4 H's. But what about this? That tells me that there are 2 of what's in the parentheses, 2 OH's. So that 2 actually distributes in and gives me 2 O's and 2 more H's. So I would have 2 carbons, 6 H's, and 2 O's. 6, 7, 8, 9, 10. So 10 total atoms. So I want you to try to write this chemical formula for vitamin B6. 8 carbon atoms, 11 hydrogens, 1 nitrogen, and 3 oxygens. Should look like that. All right, now I want you to tell me how many total atoms are in glycerin and nitroglycerin. So if you want to pause, we have 3 carbons, 5 H's, and then that 3 again distributes. We have 3 O's and 3 more H's. So a total of 8 H's. So 8, 9, 10, 11, 12, 13, 14 total atoms. And down here, I would have 3 carbons, 5 H's, 3 O's, 3 N's, and then this would give me down here at the bottom 6 more O's, because 3 times 2 is 6. So a total of 9 O's, right? These two together would give me 9. So 9, 10, 11, 12, 15, 20, so 20 atoms for the nitroglycerin. And then when we write formulas, again, you do not use 1. If there's only 1 of them, you just write the element. So we have pure substances. And within pure substances, we have elements and compounds. Then we have mixtures. And a mixture is a combination of 1 or more pure substances. I guess not 1. I guess it has to be more than 1. More than 1 pure substance. So grape juice, for example. Grape juice has water, it has sugar, it has food coloring, it has grapes, there's a whole long list of ingredients in grape juice. And a mixture can have some properties that's similar to those pure substances, like grape juice is wet, like the water that's in it. It's sweet, like the sugar that's in it. So there are two types of mixtures, homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are mixed together well enough to dissolve and appear like one substance, like gasoline, Kool-Aid, salt water, even alloys that are mixtures of two or more metals, like 10, 14, 18 karat gold. That 10, 14, 18 karat gold is actually a mixture of gold, silver, and copper metals. Then we can also have heterogeneous mixtures where they cannot be mixed together to appear. They're visibly different. Milk, blood, sand, and water, they can be separated into those pure substances by physical methods. So here's just a visual to help us see oil and vinegar dressing, how we can see that there is distinct separation. Sure, we can mix it together and it might appear mixed, but it will quickly separate. So its composition is not uniform throughout. And then here we have Gatorade. It's a homogeneous mixture. We can see that its composition is uniform. Now we can separate mixtures. Like we said, mixtures may be separated. And we're going to look at several of these throughout this course, especially in the explorations. We can separate by density, by decanting or centrifuging, by boiling point, by distillation, by filtration, using different states of matter, chromatography by looking at intermolecular forces, evaporation. You can use magnets over here to separate a mixture. And you can also filter by solubility. So here's just kind of putting together everything that we just talked about. Matter. We know matter is made of pure substances or mixtures. Pure substances we know can be elements or compounds. Mixtures can be heterogeneous or homogeneous or homogeneous. And then here's some examples. Now, physical and chemical properties. Physical properties are properties that can be observed without altering the composition of the substance. No new substance is formed. I could take my hair and I could cut it. Yes, it's shorter, but I still have hair. I did not change the substance. No new substance are formed. No substances are destroyed. Usually they are reversible. Now, not the cutting of my hair. I guess I can grow longer hair. But think about this ice cube up top. Yes, my ice cube will melt, but I still have water. I have H2O when it's solid ice. I have H2O when it's liquid. And I could take that liquid and I could freeze it and it's back to the solid state. So I'm not changing its chemical identity. Important ones. So looking at the appearance of something, melting and boiling points, density, heat and electrical conductivity, and so forth. Here's a couple examples. So butter undergoes a physical change when it's melted. Water when we boil it. Heating alcohol to a vapor. It's still alcohol. It's just in vapor form. Freezing water. Recycling aluminum cans. It's still aluminum cans or aluminum foil. It's still aluminum. Chemical properties always involves a chemical change. So it explains how one substance acts in the presence of another. New substances are formed. Old substances are destroyed. Think about burning that log. Okay, when this is all done, I do not have a piece of wood anymore. It's usually irresistible. It's usually irreversible too. For example, gasoline burning. And it is important, the composition of the substance changes. For example, iron that rusts. Chromium does not. Another example would be, so sodium metal right here, Na. Sodium is a silvery metal. It reacts with chlorine gas, a yellow gas, to produce salt. Salt, sodium chloride, which is a grainy white substance. So completely rearranging those atoms, they don't have, and it's not reversible. Here's a couple more examples. Copper and nitric acid form copper nitrate. We have the combustion of a match. We light this match on fire and we have CO2 and H2O, carbon dioxide and water as byproducts. Cooking red meat is not a reversible chemical reaction. A banana turning brown is a chemical reaction. Apples, not reversible. Cooking your pancakes, not reversible. So some clues is that there's a permanent color change, that there's a temperature change, that an odor is released or bubbles are created. Also if lighter heat in the form of energy is released. Here's some examples of chemical changes, especially cooking, burning, rusting. And that brings us to the end of today.